Good morning, everybody, or good afternoon if you're one of my afternoon classes. I had lots of requests last time that you all wanted to meet Rocky, so this is Rocky. Rocky, come here, buddy. I know you're sleepy. All right, say hi to mommy's students. Say hello. All right, he's going to stay with us at least for a little while until he decides that he wants to move. But this is Rocky. This is the guy who scared me last time. All right, so today you guys should have picked up a little notes packet on your way in, or you should have gotten that passed out to you. We're going to do just a little bit of notes today on something called stoichiometry. The muffin activity that we went over yesterday introduced this idea to you, whether you knew it or not. But today you're going to see how that muffin activity was a good intro to learning what stoichiometry actually is and practicing some actual stoichiometry with our chemical equations. All right. So what is stoichiometry? Where's my cursor? All right. So stoichiometry is using balanced equations to calculate the amount of reactants or products you have in a given chemical reaction, okay? Because if you know the quantity of one substance in a balanced chemical equation, you can figure out the quantity of the other substances in that equation, okay? Now, when or why would we use this? You can use it in manufacturing different products like soaps or paints or foods. Pharmaceutical companies, if you ever are thinking about going into pharmacy or wanting to become a pharmacist, they use stoichiometry to figure out how much of certain reactants or products they need in chemical equations that they use. It's also used for efficiency purposes in a lot of different professions to be sure that you're only using how much you really need of a certain reactant, that you're not overusing or that you're not using excess of certain things, okay? And in stoichiometry, we use things called ratios, okay? And you may have heard about ratios before. I kind of mentioned them a little bit yesterday. A ratio is a comparison of two numbers, okay? So we're going to be using ratios that we find from chemical equations to go through and use stoichiometry to calculate quantities of different substances in those reactions, okay? So there are three ways of interpreting equations, and then three ways of kind of doing stoichiometry with those equations. The first is by particle, all right? So when you look at an equation, you can look at that equation and interpret the formulas and coefficients by particle. All right, so in this example, if we were to interpret that chemical equation by particle, we would read it as 1 molecule of nitrogen plus 3 molecules of hydrogen react to form 2 molecules of ammonia. Okay, now you could increase those amounts and use the particle ratios to get a similar reaction with just increased numbers. Okay, so for example, you could say I had 10 molecules of nitrogen would mean that you need 30 molecules of hydrogen react together to form 20 molecules of ammonia. Okay, we could up it to 100. 100 molecules of nitrogen would need to react with 300 molecules of hydrogen to form 200 molecules of ammonia. Moral of the story there is that your ratios always have to occur in a 1 to 3 to 2 ratio, because in our balanced chemical equation, that 1 to 3 to 2 ratio is how our reactants and products are related. For every 1 molecule of nitrogen, you have 3 molecules of hydrogen, which gives you 2 molecules of ammonia. Okay, so that ratio has to stay constant. Another way of interpreting equations is by moles. Okay, so rather than particles, we could read that equation using moles and read it like this. 1 mole of nitrogen reacts with 3 moles of hydrogen to form 2 moles of ammonia. So in this interpretation, the coefficient tells you the number of moles reacting instead of the number of particles. Okay? This is the way that a chemist would read the equation. Okay, the coefficients stand for how many moles of that particular element or molecule or compound are reacting or are formed. Okay. The last way to interpret a chemical equation is by mass. Okay, and so in this particular interpretation, I want you to pay close attention to the fact that a balanced chemical equation has to abide by the law of conservation of mass. All right, so in this interpretation, you actually go through, calculate the molar masses of all of your reactants and products, account for the coefficients, and then see that the mass of your reactants is equal to the mass of your products. So if you look at our same chemical equation that we used on the previous two slides, calculate the molar mass of a molecule of nitrogen to be 28 grams. The molar mass of a molecule of hydrogen is 2 grams, but we have to multiply that by 3 because of this coefficient. And then the molar mass of ammonia, but we multiply that by 2 because of this coefficient here. Okay. When you go through and calculate all those molar masses and multiply by any of the coefficients that they may or may not have, what you'll find is that the mass of the reactants should always be equal to the mass of the products. That should be no surprise to any of you because that's the law of conservation of mass. That's why we balance chemical equations. Okay? This particular interpretation just shows you that. So to summarize, there are 3 ways to interpret a chemical equation. You can interpret it by particle, which is here where we read it out like 1 molecule of nitrogen reacts with 3 molecules of hydrogen to form 2 molecules of ammonia. Or you can interpret it by mole, okay, and you would know the number of moles of each molecule by the coefficients. So 1 mole of nitrogen reacts with 3 moles of hydrogen to form 2 moles of ammonia. Or the last interpretation was by mass. You can calculate the molar masses of all of the compounds, account for their coefficients, and see that in your reactants, you've got 34 grams of your reactants, 28 grams of which come from your nitrogen, 6 grams come from your hydrogen, react to form 34 grams of ammonia. Okay, so all 3 of these different interpretations are ways that you can look at a balanced chemical equation. So now we're going to practice. What I'd like you guys to do is get out your pink periodic tables. You shouldn't need your formula sheets, but you might as well grab those out. It's always good just to have both of them out. But what I want you to do is interpret this chemical equation by the number of moles as well as by the mass of the reactants. And so you're going to be figuring out molar masses and seeing if the mass of your reactants are equal to the mass of your products. Okay, so I want you guys to pause here. So pause the video, take a couple minutes, figure this out with somebody sitting around you, and then we'll go over the answer together in just a minute. Okay, so pause the video here. You guys can work out this chemical equation in number of moles as well as masses of reactants. They're going to work on their chemistry for a little bit. Yeah. Stay rocky. Stay rocky. So, okay, bye-bye, Rocky. All right, so I'm trying to get my, here we go. All right, so you guys should have had time now to go through and interpret this chemical equation by the number of moles and by the masses of reactants. Okay, so if we were to go through together now and go over the answer to both of those. First, let's do our number of moles. So if we would interpret this by number of moles, it would read out as 2 moles of hydrogen, dihydrogen, tisk tisk. All right, let's try again. 2 moles of dihydrogen sulfide react with 3 moles of oxygen to form 2 moles of sulfur dioxide and 2 moles of dihydrogen monoxide or water. Okay, so that would be interpreting that chemical equation using moles. Now, if you were to do the same thing using the masses of the different reactants, what you'd have to do is first calculate the molar mass of all of the compounds or formulas in your chemical equation. Okay, so dihydrogen sulfide has the molar mass of 34.08. Oxygen has the molar mass of 16, but that's for one oxygen atom. You have to remember that this is a diatomic oxygen, so the molar mass of that oxygen molecule is 32 grams. This is Casey, include your units. All right, and then sulfur dioxide has the molar mass of 64.06. Dihydrogen monoxide has the molar mass of 18.02 grams. Okay, now those are all the molar masses. You need to account for coefficients. So you'd multiply this molar mass by 2. Oxygen's molar mass by 3. Sulfur dioxide's molar mass by 2. And then multiply water's molar mass by 2 as well. Okay. And what you'll find when you do that is that the total mass of your reactants was 164.16 grams. And if you add up the masses of your products, you should get the same exact thing, 164.16 grams. Okay? So those are 2 different ways you can interpret this chemical equation. Either of them are completely fine. You're just interpreting it using different units. Okay? The first time we interpreted it using moles. The second time we interpreted it using masses. All right. Back to our notes. So now that we've gone over different ways to interpret chemical equations, we're going to go back to the idea of a ratio, which is what we started our conversation with when we started talking about stoichiometry. So if you interpret a chemical equation using moles, for example, you can make a ratio comparing the different number of moles of different compounds in that particular chemical equation. Okay, so I just want you to take a look at our equation here. All right, let's get my sketch back. All right, so in this equation, we've got 1 mole of nitrogen reacting with 3 moles of hydrogen to give us 2 moles of ammonia. Okay, so when you make a molar ratio, I want you to think recipe. Okay. So think about like that muffin activity we did yesterday. So in this chemical equation, there are 6 possible molar ratios. The first 2 molar ratios use nitrogen, and they compare nitrogen to the other 2 compounds. So for every 1 mole of nitrogen, we need 3 moles of hydrogen to react, okay? So in this molar ratio, you're comparing how many moles of nitrogen you have to how many moles of hydrogen you have in the chemical equation. The next molar ratio you can use or create using nitrogen would be that for every 1 mole of nitrogen that reacts, you will get 2 moles of ammonium. Okay? So there's 2 out of your 6 possible molar ratios. The other 4 would be comparing hydrogen to the other 2 formulas or compounds in the reaction. And the last one is comparing ammonia to the other 2 compounds in the reaction. Now, these are the 6 possible molar ratios that you can use when going through any sort of calculation, stoichiometry calculation with this particular chemical equation. Okay. I'm not saying you would use all of them, but those are all of the possible molar ratios you'd use. When you're doing a specific calculation, you have to consider what you're trying to calculate, and that will help you choose which one of these molar ratios you actually have to use. Okay, so we're going to go through an example in a minute. Okay, so if you interpret a chemical equation using moles, you can go through a mole-to-mole calculation. All right, so now we're going to go through an example of that. So in our example, here's our example question. Our example question says, how many moles of oxygen can be produced from the decomposition of 15.3 moles of magnesium oxide? Sounds like a complicated question, sounds like it'd be really hard to solve, but it's actually not that bad, okay? The first step in any mole-to-mole stoichiometry calculation is writing a balanced chemical equation, okay? So the first thing I want you to do anytime you are given a stoichiometry problem like this is you write out a balanced chemical equation, okay? Remember what I've been saying about formula writing? Formula writing is not going away. Okay, so you're going to write your formulas of your reactants, write your formulas of your products, and then balance. Okay, so here's our balanced chemical equation for the reaction described above. All right, so that's the first step. Write a balanced equation. The second step is to decide what molar ratio do you need to use in order to calculate the value that the question is asking you to calculate. So in this example, you are looking to find how many moles of oxygen. Okay, so I know that I'm going to be using oxygen because I have to calculate how many moles of oxygen. But the compound that I'll be comparing my oxygen to is magnesium oxide. So I know that my molar ratio is going to have magnesium oxide in it, and it's going to have oxygen in it. Okay, so I'm going to use this particular molar ratio. Now, how did I get this molar ratio? I looked at my equation. And when I look at my chemical equation, for every 1 mole of oxygen gas that is created, 2 moles of magnesium oxide decompose. Okay, so that's where I got that molar ratio. Okay. So now how do we set it up? We have our given quantity, and our given quantity was 15.3 moles of magnesium oxide, and I wanted to know how many moles of oxygen would be created by the breakdown of 15.3 moles of magnesium oxide. So I wrote my given information here from the problem, my molar ratio or conversion factor, we've talked about those as conversion factors as well, here, my moles of magnesium oxide cancels out and multiply across the top, multiply across the bottom, divide, and I get the fact that if 15.3 moles of magnesium oxide were to decompose, I would get 7.65 moles of oxygen gas. Okay. All right. So that's just one example problem. You guys are going to do another example right now. I believe in your notes, there's another example that I want you guys to try. Unless I just went through with it with you. Hold on. Okay, so we just went through our example stoichiometry problem of using a mole-to-mole ratio to calculate another molar quantity by using a balanced chemical equation. All right, so what you guys are going to do now, there are some practice problems that I want you to do for tomorrow. You have the rest of class time to work on it. If you don't finish it in class, you do need to bring it back tomorrow completed, so you do have some homework if you don't finish it. But tomorrow we're going to be correcting these together and talking again about how we use balanced chemical equations and stoichiometry to help us understand different quantities of reactants and products, so we can understand how much of certain things react and how much product they will give us. Okay, so you have the rest of the time today to work on that. Tomorrow we will come back together, go over answers to that worksheet, and kickstart spring break. Hope you guys have a great day. See you tomorrow.